Now that we have this relationship between the chemical potentials and the composition, in order to actually relate this back to temperature, what we're going to do is we're going to apply the calculus of thermodynamics to this expression. So step 4, apply calculus of thermodynamics. Okay? All right. And so what we'll do is for our chemical potential expression, we're going to take the partial derivative of it with respect to temperature. Okay? Okay? We could pull out the gas constant from the expression, and what we'll do is we'll distribute across the derivative. So d dt of mu w solid over t minus d dt of mu w liquid over t. All right, so we have this expression, and if you remember, the partial derivative of the chemical potential with respect to temperature, this, by definition, is actually the partial molar enthalpy of water over temperature. Right? Similar here, this is the partial molar enthalpy of water in the liquid phase over temperature. So that comes from, applying the calculus of thermodynamics. Okay? And so now that we have turned the chemical potentials into enthalpies, we could combine like terms. So here, there should be a square here. Okay? Could pull out the t squared term, so r over t squared, and I also pulled out the negative sign as well. And so here what we have is now the difference between the partial molar enthalpy of water in the solid phase minus the partial molar enthalpy of water in the liquid phase. Okay? All right, and so here we're looking at the difference between the enthalpy of water in the solid phase and the liquid phase, right? And you may recognize that this is essentially, what this is describing is essentially describing the enthalpy of melting, though it's the negative version of that, right? Because here we're looking at the difference between the enthalpy in one phase to another, right? And so just to make it more clear, this is equal, if I pull out a negative, this is equal to this. And this difference between the liquid phase and the solid phase, right? You're looking at the enthalpy difference. That's the same thing as saying this is the enthalpy of melting. Okay? All right, so now that we have that, we can now say that the delta HM, the enthalpy of melting, divided by RT squared, right? We turn this into that, right? And so that this, we go back here, is equal to the partial derivative of this, of the mole fraction with respect to temperature. Okay? All right. So by applying the calculus of thermodynamics, we turned this into this. Right? And then now what we want to do is we then want to just get back the natural log of the mole fraction. And so the way we're going to do that is we're going to move the partial derivative to the other side. So what we have is d ln of xw mix is equal to delta hm over r dt over t squared. So all I did was move this up here. All right, we have that. And then now I'm going to integrate. Right? And the bounds of the integral are going to go from the pure state, so pure water, to the water mixture. So if I integrate this, I have the ln of pure water on the bottom, right? And on top I have ln of the water in the mixture. Similarly, on the right-hand side, when we integrate, we're going to get negative hm over r 1 over t mix over 1 over t water pure. Okay. All right, so now what we did is we actually can now relate the mole fractions of water in the mixture to the temperature of the water when it's at equilibrium. Right? Okay? All right, one last thing. So in the end, we wanted to solve for this temperature here. So I'm going to rearrange. And one other thing I'll point out. The mole fraction of water when you have pure water, that's just 1. All right, so the left-hand side can simplify down. In any case, we could solve for TW mixture, and that's just going to be equal to this. Pure minus R delta HM ln of XW mixture. That's to the -1. And one last thing I'll do is here, we wrote everything in terms of the mole fraction of water. But of course, we can now write it in terms of the mole fraction of the actual solute in the mixture, based on that mole fraction relationship. And so in the end, we could describe the temperature the freezing point temperature now as a function of the mole fraction of salt in the mixture. Okay? And so I'll box this in. So just to clarify, this is the freezing point of pure water. And this is the freezing point of salt water mixture. Okay? And so by applying the calculus of thermodynamics, we now have a model that relates the freezing point of the mixture to the amount of salt that's in the mixture.